to the C op. Right, we take that op, we put it over here. We're currying this function. Or this functor, rather. We're currying this functor. So what does it do? It takes an object, say, I was using A for the contravariant argument, so let's use B for the covariant argument. It takes B to the functor hom blank B. So this is a functor from C op into sets. And if you just think about it for a moment, you'll remember how this thing works. It takes some A here to the set hom A, B. That's all arrows from A into B. And it takes any map from H into H prime like this. Well, these things are arrows from A into B. So if I've got a map of this shape, I can precompose with it and get an arrow from A prime into B. So that's my action now here. A prime B. The action is by H. I think I called it H upper star. That's just precomposition of some argument with H. So argument after H. And notice the change in direction, and that's why we have this op here, because this is a contravariant functor. Okay?
I missed some of that because you were
Yes?
writing it, so I couldn't see what was going on the board.
Sure.
So I missed the connection between what's on the board and what you said.
Yep. We'll have a look.
If you're standing back, quickly say it again.
I have a functor here. So I have transposed this functor to give me a functor from here into there. Okay? It takes an object B to this representable functor. And the representable functor, right, this hom functor that we talked about before, and it works like this. It takes an object A in C to the set of all maps from A into B. Okay? And now, how does it act on arrows? Well, it acts like this. If I have an arrow into A, and I have an arrow from A to B, I precompose with this arrow. And that gives me an arrow from A prime into B. Well, so this operation is going that way, where this one's going that way. So that was the definition of being a contravariant functor. And that's why we put this op here, to show that the functor is contravariant. And this is just the definition of the action. It's saying precompose with H. This map here, conventionally denoted Y, is called the Yoneda embedding. And that it is an embedding is a consequence of the Yoneda lemma, which we're going to not completely prove, but at least mention now. Yoneda embedding, let's say, is that. That's the Yoneda embedding. So here's a fact. We'll just let me just state it, and then we'll analyze it. So I guess what I should say is I know that this thing exists for general reasons. I haven't told you specifically. You have to go and unwind now how this operation acts on arrows and B, right? I showed you how it works for one particular B. How does it work if I change B to B prime? I'll let you work that out for yourself. This worked by precomposition by A. It works by postcomposition with B. That's all. So this just gave me, for each B, it gives me a functor. And now for each arrow here, it gives me a natural transformation over here between those functors. And that's a kind of getting to be a higher level of abstraction here that takes a little getting used to. But that's all it takes. It's just a little, it's one more step of abstraction. It takes a little getting used to. So anytime I have an arrow here, H, from B to B prime, I get over here, in sets to the C op, applying Yoneda, I get YB, a functor, YB prime, another one, and YH. And now this is a map of functors, so it's a natural transformation. So this is living over here. I get a natural transformation between these two representable functors, corresponding to this map between B and B prime. So it's a way of, if you like, representing C as a category of functors and natural transformations. It turns these possibly abstract objects and arrows of C into functors and natural transformations. So it's a more concrete description of this category C. As it's like if you have an abstract group, you can make a representation of it as a group of matrices and with matrix multiplication. This is representing a category as a category of functors and natural transformations between them. So that's what's going on here. And the Oneida lemma tells us that this is a very good representation. And that's what we're about to see. So the statement for the Oneida lemma is this: given any C in the category C and any functor F in the functor category, there's an isomorphism of the following form. If I look at natural transformations in the functor category from the representable functor into F, those correspond exactly to elements of the functor F at C. Okay, that takes some getting used to, but it's a nice, beautiful, compact statement. You can put it on a bumper sticker if you like. There it is, the Oneida lemma. It's probably the most fundamental fact in all of elementary category theory, is that isomorphism. It's a very useful fact. So what it's telling me is this: if I look at, here's my functor, my representable functor yc, and here's my functor f, right? And now these things have values for all objects, right? So let's suppose I have this natural transformation theta going from yc over to f. Well, in particular then, it has values yc at d, or let's, here, yc at a, yc at b, yc, where am I putting my parentheses here, like that, at c, and so on. And for every arrow, a, b, c, down in c, yc gives me arrows like this. And then F2 has FA, FB, FC. Yeah? And now the Oneida lemma tells me any natural transformation like this from yc at f is completely determined by one single element living in f of c. One single element over there. So I take my theta here, and it corresponds to something over here, some theta hat, which lives in f at c. What on earth could it be? Well, here's how you get it. You say, look at yc at c. That's a distinguished object here, right? Because the c's match up. And then apply theta. This is theta at a, theta at b, theta at c. So apply theta c to a certain distinguished element in here. What could it be? Well, what is that? That's Hom C, C. Anybody know an object in an element in that set? There's the identity is in there. The identity is in there. So take theta at C. We've got theta for everything, so take it at C. Apply it to the identity in here, and you get this kind of universal object over here. It's theta C applied to the identity at C. That's our special object here, theta hat, living in f of c. And now you use the fact that this assignment is natural, and you can basically compute everything about this natural transformation, from naturality and this given object. So that's not the proof, but that's a sketch of what goes into the proof. Okay, so now we've proved this thing, but why do we care about this? What on earth does it mean, right? I'll show you how to use it. There's one more little bit there of the Uneda lemma that I just can't help but put in. I can't bring myself to leave it out. And that is that this isomorphism here is also natural in both arguments C and F. That is, if I change C to some C prime or F to some G, then I'll get a corresponding commutative square involving that change. So there's an isomorphism natural in C and F. It's just a little bit stronger statement, but it's part of the official theory there. Okay, so what does it mean? Yep, go ahead. Yes?
Why did we have on the left side of the home rather than the right side?
Why did what?
Why did we abstract?
Okay, good question, yeah. I'll do it right now. Here's C, and here's this Uneda embedding, and I want to prove that this is really an embedding. So what does that mean to be an embedding? That's what I'm going to describe now. It takes us from C into here, right? And now the question is, why this? Why C op up here? And the reason is it makes this map covariant. If we had done it the other way around, we'd get a contravariant representation of C. We want a covariant representation of C because the way we think of this whole setup is this. C is some category that we're interested in. We want to do something with it, okay? This category, which you don't know yet, but you'll soon know, has a great deal of very useful structure in it. This set-valued functor category, it takes the structure that's available in sets and it kind of generalizes it to a category that also involves C. So when I say it has a lot of useful structure, I mean it's Cartesian closed, for example, whereas C doesn't need to be. Sets was, and this thing is too. It's Cartesian closed. It has natural numbers in it as a functor. So it has lots of inductively defined types in it. If you're familiar with dependent type theory, it has sigmas and pi's, dependent sums and dependent families. It's a topos, if you know what that is. It has higher order logic. It has an interpretation of all of propositional and all of first order and all of second order and higher order logic. So it has all this logical structure in it. It has cohomology theory, if you know what that is. It has all of this machinery in it, naturally, in a canonical way, living up in this category. Yeah? Whereas this is just any old category. And now, if we knew that this embedding was really good, and we want to study this category, we could go up here, use that machinery to prove things about the objects in C. So we take C and D, we want to prove something about them. We send them up here with the Uneda embedding, and now we use some higher order machinery up there, right? We use the polymorphic lambda calculus up there to prove something about the images of C and D. For example, we'll prove that there's a map here, just to have something, right? And now what we'd like to know is we can reflect that information back down to C. Even though the methods of proof don't exist down here in C, because C is maybe some very meager category, we can still find a corresponding thing down there. So what we'd like to know is this. We'd like to know if there's any arrow up here between these two things, up in the functor category, then there must be an arrow down here between these two things. I'm just drawing a picture of that home set, yeah? Moreover, what would be really nice is if we knew that there's a unique one down here that goes to that one, right? So what's that saying? It's saying the map that takes arrows from here, because it's a functor, any arrow down here goes to one up here. What we'd like to know is that that map is itself a bijection, right? That anything that is up there gets hit by something down here, and moreover, it gets hit by a unique thing. So that this map from here to here, which is just the Yoneda embedding acting on arrows, is actually an isomorphism, a bijection of Hom sets. And that's what it means to be, well, and moreover, that it's injective on objects, that it separates objects. And that's what it means for this to be an embedding, and that's true. And it follows in 2 lines from the Yoneda lemma. Here's proof. Let's consider Hom y, c, y, d. Well, this has the form Hom y, c, f for y, d being f. Yeah? Take f to be y, c. Apply the Yoneda lemma to get y, d of c. But what is the definition of y, d of c? It's Hom c, d. Good? That's exactly what we're trying to show here. Okay. Take f equals y, d in the Yoneda lemma. Yoneda lemma says Homming yc into any functor f gives f of c. So for f, put yd and get this. But this is the definition of that. Okay, so this machine that I was describing that we would like to have, we do have. You take any category, you take any objects in the category, you want to prove something about them, but you don't know what to do because your category doesn't have much stuff in it. Well, you apply the Yoneda embedding, you get it up here where you've got all this machinery to work with, right? Calc, everything you want. Right? It's up, yeah, because it's got like this, it's got the second order lambda calculus is up there. Right? The calculus of inductive constructions has an interpretation up here. You can use calc now to prove stuff about C. And anything that you can prove about these representable functors is true of C and D, as long as it can be expressed back down here. The thing you're trying to prove is some statement that, you know, is about arrows in here. So let me give you some examples now. Yeah. That's an isomorphism sign. It's just vertical instead of sideways. Okay. Right, it's this. So my examples, of course, are going to be these things here, because this is what I had in mind when I said you use some machinery rather than using your bare hands to prove these things. So let's prove those things. First, I need to. How are we going to do this? Okay, so do I have? Oh yeah, I have time. Before I do this, let me just remind you of something, and then I'll come back to that. Remember we said last time that the universal mapping properties that define, for example, products or coproducts or exponentials, they're kind of like rules of inference. And I wrote them in that rule of inference style with a horizontal line. Let's just recall how that worked. And then I want to express that in a different way, the same idea, using Hom sets. So for example, for products, we said a product is a thing that looks like this. If you have any x into A and another x into B, Well, a pair of maps like that, an F and a G, determine a map from X into the product, which we called FG. And moreover, the universal mapping property says, here, let's write it out right here. We'll say A cross B, B. So this is the way that this works. I say take F, take G, then there exists a unique thing here, which I called F comma G. And moreover, this composed with P1 equals F, and this composed with P1 equals G, and this is unique with that property. That was the universal mapping property, right? Universal mapping property. How do you express it as a rule of inference? Well, you say, given these two guys, you can pair them up to get something like this. But moreover, given anything like this, right, some other map here, you can compose it once with P1 to get a map from X to A, and once with P2 to get a map from X to B. So this rule of inference goes both ways, right? You can take something of this form, take its two projections, and get a pair of things like that. So the rule of inference goes both ways. But wait, there's more. Not only does the rule go both ways, but if you compose the two, you get the same thing back out, right? If I start here and I go down, and then I go back up, I get back out the same thing I started with. Yeah? So there's something more going on here than just a two-way rule of inference. It's a bijection between things of this form and things of this form, right? And indeed, if you look at the universal mapping property again from that point of view, it says, if I take things down here, like arbitrary maps here, not necessarily paired up things, I compose with P1 and P2, that gives me a pair of maps like this, right? Then that operation is bijective. Why? Well, because anything in the image, namely a pair of maps, comes from one of these, a unique one, by that operation. So that's exactly saying the operation is a bijection. Anything gets hit, and it gets hit by a unique preimage. Okay, so a third way of expressing this same thing, not to belabor the point, but it's a convenient way of doing it, is this. I look at what's above the line is this. It's the Hom set, Hom XA, Hom XB, isn't it? Well, and it's pairs, so it's that. That's what's above the line. And then there's a map going down to below the line and landing in Hom X A cross B. And how does the map work? It takes F and it takes G and it pairs them up to give me FG. And now the universal mapping property says exactly that this is a bijection of Hom sets. Good? The map coming back takes some H from X, let me do it this way, some H from X into A cross B, and it composes with P1, P2, to give me the pair of maps P1H, P2H, so that's this map coming back up. Anything of the form H is uniquely of the form pair, blah, blah, blah. Good? So I have this bijection of Hom sets. So let's look at, consider this representable functor here, Hom X blank, from C into sets. Apply to the diagram A cross B, A, B. apply this functor to that diagram. Then you get Hom x a cross b. Hom x a Hom x b. Well, but these things have a product, namely Hom x a cross Hom x b. So this is exactly this map, right? Let's apply the representable functor like that, and we just said that if this is a product, this is an isomorphism. So this condition says exactly. So the functor Hom x blank from C into set preserves products. So what we're saying is preserves products. It takes a product diagram in C to a product diagram up in sets. And similarly, I want to look at some of the other, I think I don't need this anymore. I can express all the other universal mapping properties that I showed you before like that in terms of Hom sets. And that's a good way to do it because now it's expressed in terms of functors and you can calculate with them. You know, a universal mapping property is a cute way of understanding something because it has this kind of graphical character and you get the idea, but it's not the sort of thing you can calculate with, as you learned by doing those exercises, right? You can't put them together, compose them, you get new ones, and so on. So we want to be able to calculate, and this is what these Hom functors are for. So, for example, what was the universal mapping property of the sum? If you think about it, what it says is this. You have the maps into A plus B, B. And now let's think about what happens when you Hom out of this into some other object x, then you get something like this. So what that's telling me is that if I take Hom, and I take A plus B, and I Hom into something else, well then, if I compose on the one hand with I1 and on the other hand with I2, I get a pair of maps, one from A into X, and the other one from B into X. And the universal mapping property again says that that's an isomorphism. So if you like, the contravariant representables, instead of preserving products, they take coproducts to products. And before we already displayed the universal mapping property for exponentials. We already noticed that that has the form x cross y mapping into b, has such a two-way rule, two-way bijection of x into b cross a, right? We used that last time. That's saying exactly that Hom x cross a, or x cross, a into b is isomorphic to Hom x into b to the a. Okay, so now I've expressed all of those universal mapping properties in terms of isomorphisms of certain Hom sets. And now I can use that together with the Yoneda lemma to do some of these homework exercises. So let's start with, yep.
So with the product, it looks like you define product in terms of product.
In terms of products and sets.
Okay.
I mean, I didn't define it that way, but I'm characterizing it, right, in terms of products and sets. Let's do one, we'll just do number one there. C, we want to show that C A plus B is isomorphic to C to the A cross C to the B. Oh, geez. I need one more fact. Sorry, guys. I'll do it. Let me put my one more fact here that I need. Fact. Any functor like this, which has this property that it has an isomorphism on Hom sets, will, well, any functor takes isomorphisms to isomorphisms because isomorphism is defined in terms of composition and identity. So if you have an isomorphism in this Hom set, it goes to an isomorphism up here. Conversely, if the functor itself is an isomorphism on Hom sets and you get an iso up here, well, then this was an iso down here. Why is that? Well, look. So what I'm saying is, if I start with this and I go up here and I get an isomorphism, then there's an isomorphism down here. That's my claim. Okay? So claim, if y of c is isomorphic to y of d, then c is isomorphic to d. I could leave that as a homework exercise, really, but let's just look at how it works. Okay? So the proof is by the Oneida lemma, and it works like this. You take C and D, send them up here, and get an isomorphism. Well, an isomorphism is what? It's a pair of maps back and forth, and the composite each way is the identity. So the pair of maps back and forth gives me a pair of maps back and forth down here by this isomorphism, right? And now what about the composites? Well, I take the composite of these two, and that's equal to the composite, and then I apply the functor. That gives me the composite up here, right? Well, that one's equal to the identity. The identity is in the image. It's the image of the identity down here, right? But those things now get to be equal up here. And because this is an isomorphism, they must be equal down here. And so the composite down here must be equal to the identity here, because it is up there. Good? Maybe? Is it okay? Yeah, good. Somebody said yes. One person said yes, that's enough. So I'm going to use this fact. Let me put it right there. I'm going to use that fact. If yc is isomorphic to yd, then by Oneida, c is isomorphic to d. And now I can do some of these homework problems. Where should I do them? I'll do it right here. I don't deny that it's a bit much theory the first time you see it, but hey, nothing's free, you know. The question is not, is it a lot, but is it worth it? And so that's what I want to persuade you of, that it's worth the trouble, because once you've built the machine, it works. So I want to show that c to the a plus b is isomorphic to c to the a cross c to the b. But of course, I'll use the Oneida principle now, and I'll show instead that y of c to the a plus b is isomorphic to y of c to the a cross c to the b. Well, what's this? This is Hom blank c to the a plus b. And this thing, which it's supposed to be isomorphic to, is Hom blank c to the a cross c to the b. So that's what I'm trying to show. So let's give it an argument. Well, this, we know, is Hom x cross, oh, I should have done it in the other order, shoot, because I need that first, c. I should have done that one first, sorry. Give me this one, I'll show you that one in a minute, okay? And because I'm going to use it right now. So now I distribute this in. And now I use that fact about coproducts that I can pull them out on the left of a Hom set. I can pull a coproduct out on the left of a Hom set. I already showed you before that I can pull a product out on the right of a Hom set. Hom x a cross b. I showed you that before. Hom, just to record these rules. X, A, B. That's, the rule for product says you can pull a product out on the right in a Hom set. The rule for coproduct says you can pull it out on the left in a Hom set. The rule for exponents says you can transpose up. Okay, so pull this one out. Now what should I do? Well, I can put the exponents back up. And now I can use the rule for products on the right. That's it. Whew, it's still true. You get the idea? You can reduce these things now to very simple calculations. Yep. Yes. Sure. In a sense, but only in a sense, because give me a locally small category that's not locally small somewhere else. I mean, that's a question of foundations, right? It's a question of foundations. So it depends on how you're defining your concepts. But yes. I mean, locally small is not much of a restriction, right? Every category you know is locally small. Mm-hmm.
Why do sets play such an important role here? It comes from the fact that Hom are sets.
Yeah, so if we don't need this to be sets. We could do it over any other category that has enough equipment to define the notion of a category or locally small category. We could do it into a background type theory or a background category of a Grothendieck topos or a category of topological